Now they're
Okay.
coming on screen.
Okay. Okay. So good afternoon, everyone. I am, as Ved correctly said, that I am Ravi Muzaffar. I am today going to discuss about the FEM studies for optimized design of nitinol-based porous metallic fibrous materials. So throughout the entire presentation, this is how I will maneuver the presentation. I'll start discussing the porous materials first, and then define the porous metallic fibrous materials, which are actually a little different from the conventionally used porous materials. Then it is very important in case of porous metallic fibrous materials to know what are the materials from which it is made up of. And then more specifically, I'm going to discuss about shape memory alloys, for which nitinol is one of the representative elements. And then what are the Ansys models for shape memory alloys, and how I have used that for modeling the or for optimizing the design of porous metallic fibrous networks. So, actually, what are porous materials? Porous materials are the materials that have hollow spaces or voids present in them. The voids can either be interconnected or they can be separate. Now, the characteristics of the porous materials due to their porosity is that they have low relative density, their permeability is high, and they have low thermal conductivity. Also, their surface to volume ratio is high, and they are good in energy absorption. Conventionally, if we see that how are the porous materials made, it is seen that about 41% of the porous metallic materials are made by powder metallurgy route. Now, what is powder metallurgy route is that you have to take the powder of the metals, and then you have to mix them, and then compact them, and then finally sinter them, so that you have pores present in the entire structure. So 41% of the porous materials are generally made from the powder metallurgy route, although there are other routes available also. For example, space holder method, wherein you use a space holder in the powder, and then you somehow take that space holder out, so that the cavity left is created, it can be considered to be a pore. And the commonly used space holders are, for example, NaCl that can be leached out using water. So there are different other ways, but conventionally the most commonly used, as you might be aware, the most commonly used technique to make the porous materials is the powder metallurgy route. So what are the applications of these porous materials? And because of their lightweight, they are used in the core of the structural sandwich, as can be seen due to their high surface area. They're also used in fillers and filters. And because of their presence of the pores in them, they're also used in biomedical applications. So how do they help in here is that the presence of pores ensures that there is connectivity between the osteoblasts, and as a result of which you have a connective network of tissues formed, resulting in the better application of these porous materials as biomedical implants. Also, because of their large surface area, they are used in catalysis and electrodes. And one important parameter is that their porosity can be controlled also, and they're also used in heat exchangers as because they have low thermal conductivity. So commonly known porous materials, as you might be aware, are the foams. Foams, as I said, are made from generally from the powder metallurgy route, and wherein their powders of the metals are mixed, and then they are finally sintered after compaction, obviously. However, there are certain drawbacks associated with the foams. One of the most important drawbacks is the compositional inhomogeneities, as a result of which their strength is a bit lower than what can be what is theoretically possible. Also, these have macropores as well as the micropores present in them, as a result of which, again, their strength and ductility are affected. So, in order to avoid all of these things and still get a metallic porous material, we have porous metallic fibrous networks. Now, what are porous metallic fibrous networks? These are the networks, or these are the materials that are made by the metal fibers. The metal fibers are aligned in any specific direction, or they can be stochastically arranged, and then they are compressed and mostly sintered. It may happen that the metal fibers, the template of the network is such that you just wind the fibers together in some random pattern or a specific pattern, and then compress them. And even after compression, you do not need a sintering, because the metal wires are already wound with each other. As a result of it, you do not need extra strength to be imparted to them. However, if you just randomly place them in a die, and then in any random fashion, and then compress them and finally sinter them, it helps in imparting the strength due to fiber joint. And one of the important advantage of these fiber networks is that their porosity is up to can be as high as 98%. Now, with the conventionally made porous materials, you see that it differs depending on the method that we have used to or chosen to make the porous metallic material. And I don't think it reaches quite this high, or 97%. Obviously, it is possible, but 98%, and that too open pores. Now, what is, you have to understand that in porous materials, there are two types of the pores. We have closed pores as well as open pores. In closed pores, what happens is that one side or one face, at least one face of the pore is closed, but in open pores, all the faces of the pores are open. So what the advantage of porous metallic fibrous network is that all the pores are open pores, because we are taking into account the metal fibers only. So there is fiber bonding that is happening, resulting in the creation of open pores. And the open pores are very controllable, meaning you can control the porosity of the open pores depending on what is your application that you want to use these porous materials for. Also, another important advantage of porous metallic fiber networks is that any metal that can be converted into a wire or a fiber can be converted into a porous metallic fibrous networks. As such, if we see the research that has been going on or that has already been done in these networks, so we see that porous metallic fiber networks of copper, stainless steel, aluminium, magnesium, even shape memory alloys have been made, just because they can be converted into wires, and then the wires can be arranged in any network that defines our specific requirement. Again, if you see in this figure, we see that these are the fibers, the metal fibers, and you see these refer to the joints that are that are formed after the fiber and fiber interact with each other, and then they are made to sinter. Maybe in this image it is quite visible, the joint between the fibers. So the joint between the fibers provides the required strength that is required, that is imparted to the porous metallic fibrous network. And it is quite visible in these images that these are the metal fibers, and the metal fibers are sintered together so that there's a joint formed between them. Now, these porous metallic fibrous networks have controllable porosity, meaning you can even change the porosity of these networks depending on whatever is the requirement. And it is seen especially for aluminium, that even with the same porosity, the energy absorption of porous metallic fibrous networks is almost 10 times higher than that of the conventional porous material, that is the foam. Also, they have good energy absorption, and they have ultra light structures because of the presence of porosity, and better ductility and strength as compared to that of the conventional foams. Now, we have to understand that there are certain factors that affect the properties of porous metallic fibrous networks. First are the structural parameters. The structural parameters include the fiber length, the diameter of the fiber, the aspect ratio of the fiber, the orientation of the fiber, as well as the porosity of the network. The fiber orientation and the porosity come under the network architecture. Also, we have to understand that these structural parameters should affect all the porous metallic networks in a similar manner, meaning it would not depend whether your network is made up of copper or it is made up of, say, aluminium or any other material. As far as the structural parameters are concerned, all the effect of these parameters should remain constant. Now, there are processing parameters also. Now, if you are doing sintering of these materials, for example, then what is the sintering temperature, what is the sintering time, the compaction pressure, they also affect the overall properties of porous metallic fibrous networks. And obviously, the most important thing is what is the fiber material made up of. If this is what defines the ultimate baseline of the properties of these networks. So generally, in a very broad sense, we can divide the entire materials into two broad categories. We can say that we have non-transforming fiber materials and transforming fiber materials. Here, I'll just give a brief description of these materials. Non-transforming fiber materials can refer to the fiber materials which do not show change in phase whenever they are loaded. So you have a single phase when they are loaded, and after loading also you have a single phase or the same phase. But what happens in transforming fiber materials is there is actually a phase change during loading, and this is quite to understand the analysis and to understand what is happening in transforming fiber materials is quite interesting. So to give you a glimpse of the structural parameters, because I'll be discussing this and how do we relate it with especially the FEA analysis, the Ansys analysis that I have done. So if we consider this to be a porous metallic fibrous network, wherein these are the fibers and these are referred to the joints between the fibers, so we can define fiber diameter as the diameter of the fiber. The other structural parameter is the fiber length, that is the length between two bonds or two joints. And then we have fiber segment aspect ratio. Then you have the fiber orientation, meaning with respect to the loading axis, what is the orientation of the fiber? This is one of the most important structural parameters that we have studied, and we have found out how it affects the overall properties of the porous metallic fiber network. So as I told you in the start also, that it is not the network, whenever the template, the architectural template is laid out, it is not necessary that you have fibers laid in certain specific directions. They may be stochastically arranged, randomly arranged. And it is very important now, after the analysis that we have done and after many people have studied this, that this orientation also affects what are the overall properties of the network. So to understand this is also critical. And then you have the tortuosity, which refers to the uh, ratio of the curved cross section to the straight cross section between two joints or 2 points. So these are the parameters that are independent of the material that we are going to use in order to form the porous networks. So the factor, that the influence that they exert should be same irrespective of the material that we are using. So one of the most, as I already told you, one of the most important parameter that affects the properties is the orientation. So as you can see in these two figures, these are the copper porous metal fiber sinter sheet, meaning that the copper fibers have been used and they are compacted and sintered to form the porous metallic fibrous network. And here the copper fibers are randomly arranged in any manner. They're just placed inside the mold, compacted and sintered to form this sintered sheet. If you compare it with this case, in this particular case, what people have done, both obviously done by the same group of researchers, wherein they have used the copper fiber, the same copper fibers, but here they have arranged the copper fibers parallelly to each other, meaning they are not randomly arranged. They are following a certain ordered arrangement. And when they check the tensile strength of these properties, it is seen that this oriented linear porous metal had the highest strength, even if the holding time, the sintering time was different. We see that it is considerably higher as compared to the sheet wherein we have used the fibers that are oriented in any random direction, even at the same porosity levels. So it is very important, therefore, the concept of the laying out of the fibers, the architectural template, it is very important to understand how that affects the overall properties. In this particular case, the mechanical properties, but then there are people who have studied other properties as well. So now for the processing parameters, that was about the structural parameters. In the processing parameters, as I already discussed, it is the sintering temperature and time. So from this figure, we can see that if we are taking the networks and then we are sintering them at different temperatures, we see what happens, that with the increase in the temperature, as the temperature increases from 700 to 800 to 900, we see that with the increase in the temperature, the strength also increases, right? And this is probably because of the increase in the contact joints. The fiber joints are increasing, therefore the overall strength is also increasing. However, if we see at this constant temperature, but the time is changed, we see that with the increase in the time, there is grain coarsening that is happening, resulting in decrease in the strength, as is evident from the figure. Here, the temperature is 800 and the time is 30 minutes. The strength is around 0.9 to 1 megapascal. However, if the sintering time is increased to 60 minutes, we see that it has considerably decreased to about 0.6 or 0.7 megapascals because of the grain coarsening. Now, if we see what is happening due to compaction pressure, we see that as the compaction pressure is increasing, as is visible from this figure as well as the graph, the porosity is reduced. So you see, as I'm increasing the pressure, the compaction pressure, the densification is happening, as well as resulting in decrease in the porosity of the material. So now if we consider the material parameters, as to how the material parameters define the properties, we see that as I already told you, that it can be generally divided into two broad categories. First are the non-transforming fiber materials. These are the fiber materials that do not show any solid state phase transformation whenever they are loaded. So they follow the conventional deformation behavior, meaning when we are loading them in a tensile manner, they will elastically deform. After they have the strain hardening condition, they will strain harden, and finally necking will take place and the failure will take place. This is the conventional deformation behavior of non-transforming fiber materials, and it's irrespective. All the conventional materials show this type of the curve on the degree to which they what is the slope, the strain hardening component, the necking, all the degree will change, but the generalized concept is the same, meaning it will elastically deform and it is followed by plastic deformation, finally failure. So we see that these porous metallic fibrous networks of the non-conventional non-transforming fiber materials are also made. One of the examples is titanium, stainless steel, and even aluminium. So in these two particular cases, you can see that actually the fibers are wound in certain helical patterns and then they are compressed. So it's not necessary that you follow a specific route to make these porous metallic fibrous networks. You can have your own architectural template depending on the strength that you require and the application area, obviously, of that material. Now, what is more important is to consider the transforming fiber material. Transforming fiber materials are the fiber materials that show solid state phase transformation from one phase to another whenever they are loaded. And the representative example of shape memory materials or the transforming fiber materials is the nitinol. So we see nitinol or the shape memory materials, they have this characteristic phase called the austenitic phase, which is stable at higher temperatures. And they have another phase called martensitic phase, which is stable at lower temperature. So any temperature fluctuation, meaning if you are decreasing the temperature, the austenite gets converted into martensite. And whenever we are heating, the martensite gets converted into austenite. Also, what can happen is austenite can get converted into martensite by loading only and not by the intervention of temperature. So we see, for example, if you can see in this particular example, this pin paper clip is made up of shape memory materials, and we see that whenever it is deformed, it deforms like any other normal material. But once you are applying heat to it, the martensite gets converted into austenite and it regains its original shape back by the application of temperature in this particular case. So it is also seen that normally for the materials, for all the conventional materials, the elastic strains are very small, about 3%, 4% maximum. But for shape memory materials and nitinol, it is about 8%. So the recoverable elastic strains is about 8%, which helps in the functioning of bone implants, as they apply a constant compressive force to the bone fracture. And hence they are used in many biomedical field. So one of the important things that we have to consider before we actually discuss about what is happening in the analysis of these networks is that apart from austenite and martensite, they also have another phase called R phase, and we have to see at which temperature ranges these phases are stable. So normally what happens is that whenever we are heating, as I told you, that austenite is stable at higher temperature and martensite is stable at lower temperature. So what happens is that whenever we are heating, there is a temperature wherein the conversion of martensite to austenite takes place, and that is referred to as austenite start temperature. And then there is a temperature which is depicted by this peak. And then there is this temperature where the transformation from martensite to austenite is complete, and that temperature is referred to as austenite complete phase. Similarly, in the during cooling also, there is conversion from austenite to martensite, and you get the characteristic transformation temperatures, which depict what is the temperature at which a particular phase is formed. And these we obtain from the DSC plots. Now, there are two important properties of these shape memory materials. First is the superelasticity or pseudoelasticity, and the second is shape memory effect. What are these properties and how are they modeled is what is actually very important to consider. So this just gives you a brief description of the shape memory alloys. As I told you, that austenite can get converted into martensite directly whenever it is loaded. So whenever we are loading austenite, it gets converted into martensite. Obviously, the temperature at which this transformation takes place is higher than austenitic finish temperature, meaning a temperature where complete austenite is formed. So whenever we are at this particular temperature, whenever we are loading austenite, we see that because of the loading, there is a phase transformation. Austenite gets converted into martensite. And this is referred to as pseudoelasticity or superelasticity, and it is one of the most important characteristics of shape memory alloy. Apart from pseudoelasticity, we also have shape memory effect, one-way shape memory effect or two-way shape memory effect. Shape memory effect refers to the conversion of austenite to martensite whenever there is decrease in the temperature, and then reconverting it back whenever there is increase in the temperature. So what this usually takes place when a temperature is less than the martensitic finish temperature. So we also, for the analysis of these materials, we have to take into account what is the temperature at which the transformation is taking place, or what is the temperature wherein we intend to use the materials. Then we have to change the processing parameters so as to fit those temperatures into the temperatures wherein we are going to use them. The transformation temperatures need to be fit to the working temperature so that it becomes really usable. So as I told you, that the two important characteristics of shape memory materials are the shape memory effect and the superelasticity. So this is actually the stress strain curve which describes the superelasticity of the material. So what is actually happening, as I told you, that at a temperature greater than the austenitic finish temperature, if we load, okay, test temperature is kept at a temperature which is normally 15 degrees higher than the austenitic finish temperature, so that you are sure that entire phase is austenitic in nature. So when we start loading the materials, we see that initially it is the austenite, because we are taking a temperature greater than austenitic finish temperature. So the stable phase is austenite only. So initially what happens is that austenite, the elastic deformation of austenite is happening. Finally, there comes a region referred to as plastic region, where the stress remains almost constant, and it is in this region that there is a transformation from austenite to martensite. So when what this plateau region depicts the transformation of austenite to martensite, and then when we continuously start to apply the load again, then there is elastic deformation of martensite that is happening. At this point, if we try to unload the material, what will we see is that for the unloading there is elastic strain recovery, and then whenever we are, then there is again transformation of martensite back to austenite, right? And this, but in lower plateau zone, where the martensite that is formed is converted back to austenite, and finally you have elastic recovery of austenite. So this is a very characteristic curve, and we need to understand and see the stresses which are important for the transformation of one phase to another phase. At this particular value of stress, wherein the austenite gets converted into martensite, this value of stress is very important, and where it ends, where the transformation of austenite to martensite ends, is also very important. Again, where the reverse transformation takes place, meaning the transformation of martensite to austenite is started, and at what stress is it complete, is also very important to consider. And again, the strain, the transformation strain or the plateau strain, meaning the strain values wherein one phase converts into another phase, is also important to consider. All these are important, and the parameters that are actually used in the Ansys model to depict or to make this particular, to do the analysis of these kind of materials. So this was about super elasticity. This is what I would focus on. However, there is another effect also which is present. The module for shape memory effect is also present in Ansys, and that is the shape memory effect. In the shape memory effect, as I told you, that this particular effect comes into being whenever you are loading the material at a temperature less than the martensitic finish temperature. When the temperature is less than the martensitic finish temperature, it means that you are sure the phase that is present is martensite only. So what is actually happening initially when you are loading, there is elastic deformation of martensite that is happening. And once the elastic deformation of martensite happens, then there reaches a stress, a critical value of the stress, where the martensite, the twinned martensite, gets converted into detwinned martensite. And finally, there is again elastic deformation of detwinned martensite, and then they are unloading it. After unloading, you see that there is some remnant strain present in the material, and this remnant strain is recovered by heating. So whenever we are heating, the remnant strain is recovered, and you get the original shape of the material back. So this is referred to as shape memory effect, wherein you use heat to get the original shape back, whereas when we only use the stress and the loading parameters, we consider that to be super elasticity. So we have to see what is important in transforming fiber materials is that they are relatively difficult materials to work with, considering that no two fiber, if we are talking about nitinol, no two nitinol materials, if taken from different suppliers, even from the same suppliers and different batches, they will not perform in the same manner, because their properties are very much dependent on the thermomechanical history that has been provided to them. So you see, whenever the percentage of cold deformation is increasing, we see that here the characteristic transformation plateau is observed, or the plateau strain, you can easily see that there's a transformation happening whenever we are loading. But as you see, with the increase in the cold deformation percentage, you see that this is lost. This characteristic stress strain uh, plot of the shape memory materials is lost, and it starts to behave like a normal conventional material, wherein elastic deformation is followed by plastic yielding and plastic deformation, and the final fracture takes place. So this is very important. What is the percentage of cold work that is given to it? And we see that this effect can be negated whenever we are doing the annealing treatment. So we have to specifically, the processing of these fiber materials is very difficult, and we have to see what is the cold deformation that is given to it, and what is the annealing treatment that we are going to do. Do we have to solutionize it, or do we have to partial annealing, wherein we do annealing directly after cold working? So we have to be very cautious about all these things, and then decide on carrying out the analysis of these materials. So actually, nitinol, the porous fibrous materials of nitinol are also made. As you can see, these are the compacts that are made from the and fibers of nitinol, and you can see there's a bond. This shows fiber to fiber bond between the nitinol wires, and we see these are two different compositions of the nitinol material, porous metallic fibrous material, and we see that there is characteristic transformation of austenite to martensite taking place, probably not like a very straight line depicting the transformation stress, but a very rigged line, more or less straight, depicting the transformation. And we see that there is a 5.9% recovery whenever we are heating it after we are unloading it. So similarly, in this particular case also, we are able to see that there is recovery. There is superelastic shape memory recovery whenever we are giving the temperature to it. So our job is to find out what are the mechanics that involve the deformation of all these types of the material. So considering that we have this three-dimensional multi-layer transfer, multi-layer porous metallic fiber, we can consider it to be made up of single layers of many single layers of the porous metallic fibrous networks. Okay, and then they are joined together. If we take one layer, we see that this is one layer, and we see that if we consider this to be the loading axis, we are already familiar with the structural parameters that determine the properties. For example, the fiber diameter, the fiber inclination angle, the segment length, that is the length between two bonds. And then we see we are actually tracing it down so that we can find out what is the single structural parameter that affects all these properties. And one of the most important structural parameter that we have found to affect the property is the fiber inclination angle. So what is the inclination angle of the fiber with respect to the loading axis is what we are going to study, and we are going to see how it affects the overall properties of the material. So, for example, if we are doing it for a non-conventional fiber material first, and we see that this is for a single fiber, and it is non-conventional, meaning this particularly has been done for copper, which shows a general parameters like elastic deformation followed by plastic deformation and fracture. We see that there is a great change whenever we are changing the fiber inclination angles. We see that if we want to quantify the effect in terms of fracture force, yield force, as well as the displacement at fracture and displacement at yielding, we see that there is change in all these parameters. The yield force continuously decreases whenever the fiber inclination angle is increasing, and the displacement till failure is increasing whenever the fiber inclination angle is increasing. So all these things have been seen, has been observed experimentally, and then in order to understand what actually is happening, we also have developed an analytical model and seen that it is actually the axial force that is increasing and the bending moment that is increasing, resulting in the overall decrease in the yield force and the increase in the overall deformation. So for that, we compared the result of the experimental result with the analytical model, and we saw that showed a very good correlation. With the increase in the fiber inclination angle, the fiber yield force actually decreases. And then when we have to compare it with the displacement at yielding, also we saw that displacement at yielding increases with the fiber inclination angle, and it matches well with the experimental results. So the same thing when we have used it for shape memory materials. So it, as I told you already, that the properties of the shape memory materials are very much dependent upon the thermomechanical history. So you cannot straight away use the fibers for making porous metallic materials. You have to see what is their condition, what is their history, is there any scope of improving their properties. So what we did was we took the material that was provided to us, and we saw that for the as received condition, we did not see any characteristic transformation plateau for the material, for the wire that was provided to us, meaning that it was simply in the cold work state and it needed processing changes so that we have the characteristic plot. So if you see this closely, I have just enlarged it. You can see that as received material did not show any characteristic plateau, but however, with the annealing at different temperatures, we were able to observe quite clearly that there is a transformation happening at certain values of the stress. And with the increase in that annealing temperature, we see that that stress that is required for the transformation is continuously decreasing. So again, to quantify the effect, we have seen the fracture stress, what is the strain at fracture, what is the plateau stress, meaning what is the stress at which the transformation begins, what is the plateau strains, how much strain is required for the complete transformation of one phase to another phase. And we have seen that with the increase in the annealing temperature, the plateau stress decreases, as is quite clearly observed here. The plateau stress is decreasing, whereas the plateau strain is increasing. And if you want to see the fracture stress, that is also decreasing, and the strain or fracture is highest for the material which is recrystallized completely. So at 600 degrees Celsius, the fiber is completely recrystallized and it has the highest fracture strain values. Now, if you are doing the superelastic test refers to the test wherein you are unloading the material after about 6% of the strain is applied to it. So we see again it is dependent on the temperature fluctuations. It is dependent on the annealing temperature that we are giving it to them. These tests are quantified on the basis of upper plateau stress, which refers to the value of stress at around 3% of the load during loading, and lower plateau stress, which refers to the stress which is 2.5% at a strain of 2.5%, but at unloading. So, and the residual strain, meaning what is the strain that is left after the material has been completely unloaded. And obviously the hysteresis, meaning what is the difference between the upper plateau stress and the lower plateau stress. So we see that with the increase in the annealing temperature, the upper plateau stress as well as the lower plateau stress decreases, as is completely shown here. And we see that whenever we are increasing the annealing temperature, the recovery strain is also decreased. For this particular material, whenever it is in completely recrystallized state, we see that there is no recovery taking place, very negligible recovery taking place, as is seen here also. However, for all the other cases, we see good recovery taking place whenever we are unloading it. So again, we have selected one particular condition, the optimized condition, wherein the strength was also optimum and the loading condition was also optimum. And we have seen the effect of, again, the fiber inclination angle. And we have seen that with the increase in the fiber inclination angle, the plateau stress decreases, whereas the plateau strain increases. Whereas if you want to see the effect on fracture stress, we see that it decreases, whereas the strain at fracture increases with the increase in the fiber inclination angle. Again, if you are doing the superelastic tests with different fiber inclination angles, we are seeing that the upper and lower plateau stress decreases, whereas the recovery strain also decreases. So it is actually quite important to consider, because as I told you already, in a porous fiber metallic materials, we have two alternatives. Either we make it very stochastic, meaning we randomly place the fibers in any random direction, or you can make it ordered also, depending on whether we want it to be more ductile or we want it to have more strength, or a optimized condition of both of them. We have to specify the inclination angle that we are going to give. Also, when we are using shape memory materials or the nitinol, we also have to be very considerate of the fact that what is the residual stress left, or what is the residual strain left, meaning how much would it change its shape after it has been loaded and unloaded. So that also we have to take into account, and that is seen to be very much dependent on the inclination of the fiber network. So it is very important that we have to see the template of these porous materials, what is the architectural template, how we are making these materials. So now we have used the same model, that analytical model that we had developed earlier, and we have seen that it is quite it fits well with these materials also. That is, the transformation force decreases with the increase in the fiber inclination angle. Now, if we have to model especially the nitinol materials, for other, I believe that for all the other materials you already know how to model these networks. For the Ansys, if you are using Ansys and we have to model particularly the shape, the super elastic effect of nitinol in it, in general we know that what are the steps that are followed in Ansys. We have to specify the material parameters, we have to specify the geometry of the component that we are going to test on, we have to specify the meshing, we have to specify the boundary conditions, and finally we get the result. So all these parameters are important. So material parameters, we know in this particular case there is a specific model for nitinol for shape memory alloys present in the Ansys, wherein we have this characteristic. With this characteristic plateau is what is this characteristic plot is what is utilized in order to get the input parameters and input it into the Ansys, so that the same super elasticity can be applied in Ansys. So as I told you, that there are certain stresses that we have to be very aware of. That is, the first is the stress wherein the austenite to martensite transformation starts to begin, and then is the stress wherein the austenite to martensite transformation is complete. Then on unloading, we have to see what is the stress where the reverse takes place, meaning the martensite gets converted into austenite and vice versa. And then we also have to see what is the stress at which the martensite to austenite transformation is complete. And again, we have to see what is the strain that is utilized in all this. What is the plateau strain? That is the strain which corresponds to the transformation of austenite to martensite during forward deformation, and martensite to austenite in the reverse deformation. this is actually what is happening inside the material. So you have austenite being converted into martensite and back into austenite. So this is what is happening. This is depicted as this curve. So what do we see in the model that Ansys has provided us? We have to see what are the parameters, the input parameters. So this is generally taken to be the curve, which is representative of the parameters that we are going to input for the nitinol materials. And in this, as I already told you, the first parameter, there are usually the 6 parameters that we have to input. The first parameter is the stress corresponding to the transformation of austenite to martensite, and that is depicted as sigma SAS, where sigma S is the start of the stress required for the transformation of austenite to martensite. Okay, and this is in the forward deformation, meaning whenever you are loading it. And the second stress is the stress wherein the transformation from austenite to martensite is complete, and that is given by a sigma FAS, where F refers to the finish of austenite to martensite conversion. So these are the 2 parameters that need to be input. Third, that need to be provided. The third parameter that is required is this stress, that is the stress at which the transformation of martensite to austenite begins. That is sigma S, that is the stress at which the transformation is started from martensite to austenite. And then what is the stress at which this transformation is complete from martensite to austenite on unloading. And then these are the 4 stress parameters that are required. The 5th parameter that is required for the analysis is the strain. Is this strain, this transformation strain, meaning the strain that is important, that is required for the complete transformation of one phase to another, either during loading or due to unloading. And the 6th parameter is the alpha parameter, which is going to tell you what is the material response in tension and compression. If there is any material difference in the material response from tension and compression, you have to use C6. So I have used, so we, for first case I'll show you is the case wherein I have taken it from a paper which has this particular, so these group of researchers did their analysis, did their experiment on a wire, on a rod of the shape memory alloy, and found out what is the corresponding super elastic curve, and then they tried to model it on Ansys and tried to see if there is any variation, or if we are, verify the model for that. So these are the parameters. So you can see it here. If you go to the wherein we have to input the material properties, we see that there is a module for super elasticity, and the first parameter that you have to input is the stress that you have to, the SAS refers to the stress for austenite to martensite start stress, and FAS refers to the stress that is the austenite to martensite finished stress, and then you have SA, which here S refers to the martensite. So SA refers to the stress that is required from martensite to austenite conversion, that is the start of the stress. FSA refers to the stress that is required for the conversion of martensite to austenite, and whenever that transformation is complete, what is the stress? And finally, what is the epsilon? What is the strain, transformation strain, and alpha if there is any change in the compression and tension plots. So we see that these are the results that they obtained. So for a rod of say 10 cent, I think they used 10 centimeter long rod wire with 2 centimeter thickness, and this is what they obtained: the total displacement in Ansys and the equivalent stress in Ansys. And when we tried to model it ourselves, we saw that this is the stress strain plot that they observed, and this is what we get using the same model. Okay, so here these are the stresses that you have to give in, and the strain then you are able to get, which corresponds well with whatever is experimentally observed. So these are actually some of the results that we did or on our own analysis. So the black one is, again, this is done for because we are going to use fibers in the porous metallic fiber network. So it is important to determine the properties of individual fibers first. So for that case, what we did was we took the fiber and then we tested it in a tensile manner. And you can see all these intrusions and what Luder bands being formed, which are very depictive of the transformation that is actually happening. That there is Luder band transformation type of motion for the austenite to martensite conversion. So experimentally, this is what we have obtained, and if you are doing Ansys, you also see that this is the result. So this is what you are obtained from Ansys, and when you compare the two, we see a very good correlation between the two parameters in the two plots. So what we tried to do was that in this particular case, this was the data that we obtained when we took a particular value of the processing condition, meaning a particular temperature and a particular annealing temperature and particular annealing time, and we saw what is the effect of fiber inclination angle on the overall properties of the material at different inclination angles, as is clear from this figure. And then these are the tensile test till failure. So at this particular where you observe the load drop, here the fiber is failing. So if you observe the component, the part, the fractured end of the fiber, we see that there are many dimples being formed inside the surface, characteristic of the ductile fracture of this particular type of material. And when we tried to see the superelastic plots, we saw that what is happening to the superelastic curves. And we tried to model one experimental plot with the Ansys plot, and then we tried to find out what it would be for the fibers that are loaded at different inclination angles. So we saw that whenever we are, so here it is, there is the experimental and simulation correlation between for the superelastic curves, and we saw what happens here. The 0 degree here refers to the wire which is along the loading axis, and then we are changing the fiber inclination angle, because I already told you that in porous metallic fibrous networks we have different inclination angle of the fibers, and it is very important to understand how they affect the overall properties. So we saw the superelastic curves of these different material parameters, and we saw what is happening to the upper plateau load, lower plateau load, and hysteresis, and it very well conforms with what the experimental tests were done, but on under other condition, that the upper plateau stress as well as the lower plateau stress decreases, as well as the hysteresis decreases, and the plateau range, forward plateau range, as well as the reverse plateau range decreases, as well as the displacement for transformation, that's the total transformation, increases. So again, this was for a single fiber. Now the second step after going from single fiber is to make a single layer network, because the combination of single layer network would give us the multi-layer network of nitinol. So for that, we considered a simplistic case wherein we took 2 vertical fibers and 3 horizontal inclined fibers. And this, for this particular case, I've shown it to be 45 degrees, but then we changed the inclination angles and saw what are the different parameters, what are the different effects of that change. So the overall length of the network was kept constant at 25 mm, and the width of the network was kept constant at 4 mm. So we have, as I already told you, we have 2 vertical fibers and we have inclined fibers, 3 inclined fibers in this particular case. And then we have vertical segment length, which refers to the distance between the vertical fibers. And then we have inclined segment length, which refers to the distance between what is the length of the inclined segment. And again, we modeled the experimental, we used the model, we did the experimental analysis of this, and then we modeled it with the Ansys so that we can do it. We do not have to make, because these fibers, the nitinol fibers are quite expensive, very expensive rather. So we cannot do all the tests experimentally. We did it for a single test, and then we made the model, saw that the model correlated well with the experimental results, and then for all the other architectural templates, we used this analysis and tried to find out what is actually happening when we are changing the parameters of this single layer network. So there are many variables in a single layer network. It's a separate issue. 1 second, please. So there is many variables. For example, we have porosity, we have the vertical segment length, that is the vertical length between 2 inclined segments. We have the inclined segment length, which is the horizontal length between 2 vertical fibers. And then we have what is the inclination angle of the fiber that we are going to take. All these things, what is the length that we are going to take, what is the width that we are going to take, what will be the corresponding porosity. All these things have to be modeled and seen what is the effect of all these parameters. For that, we defined this a separate analysis wherein we try to find out what are the parameters that actually affect the overall properties, and if we consider this model to be correct, and then what are the implications of that. So first is obviously porosity in a single layer network is very important. We tried to model using Ansys, using the same module that I tried to show you earlier, and we saw that with the increase in the porosity, the number of fibers, the number of inclined fibers actually decrease, and we saw that with the higher fiber inclination angles, the number of inclined fiber is more at a particular porosity. And when we tried to see what is happening with the porosity, we saw that with the increase in the porosity, the maximum force before unloading and as well as the hysteresis is 0. Whatever the force that we're obtaining is not 0, is decreasing with the increase in the porosity. Similarly, we tried to find out what is the effect of inclined segment length in a single layer network, and we saw that with the increase in the porosity, the inclined segment length for all the different fiber inclination angles increase. And then we tried to find out what is the effect of inclined segment length and the maximum force as well as the hysteresis. We saw that with the increase in the inclined segment length, the maximum force before unloading decreases, because if you increase the inclined segment length, it's the porosity that is increasing. When the porosity is increasing, the load that is withstood by the network is obviously decreasing. Then we try to find out what is the effect of number of inclined fibers. So you have different inclined fibers, and then we saw that with the increase in the inclined fibers, the maximum force before yield unloading as well as the hysteresis increases, and it is highest for the condition wherein the inclined fibers have lower inclination angle. So all these analysis is obtained from Ansys and not done experimentally. So from all this, we come to the conclusion that for the shape memory alloys, we can model, I have shown super elasticity, but we can also model shape memory effect using the Ansys. And then the modeling parameters that are required, they include the austenite to martensite start stress and the austenite to martensite finish stress, as well as the martensite to austenite start stress, the martensite to austenite finish stress, the transformation strain, and the difference parameter. That is all from my side. Thank you so much.
Yeah. Am I audible?
Yeah, you are.
Yeah. So thank you, Dr. Arvi. Yes. So if participants have any questions, they may please ask. Okay. How many of these participants are working in the area of materials, or maybe say uh, uh, okay. So Dr. Arvi actually works in the area of materials engineering, you can say. So like mechanics of different materials, like one of the types of materials could be porous materials. So she has worked extensively on these materials. So anybody who actually are interested to work in these areas, these studies should be, and approaches and how to use this FEA, I would say like they are really helpful. Uh, anyone has any query or something? Okay, so actually I have one query.
Yes.
Yeah, so you basically was showing like one plot, and you basically found one elastic modulus. Uh, on x-axis you have some values like recovery rate or something.
I'll share the slides. You can tell me
Yes.
which figure I was referring. Mm. Is this the one?
Just a minute, not no.
One second.
I think after that. No, not this, not this.
This?
No. Next slide. Next. Next. No. In the slide where you basically calculate your elastic modulus.
Modulus? I don't think I've calculated modulus.
In one slide you have like I think before modeling these things, I think before that.
This?
Yes, this one.
Okay.
Now you see, if you look at these two plots, So you are showing like elastic modulus of say 0.95 in the left one and 3.03 in the right one. Uh, now, so generally we define modulus with the initial slope for a straight versus strain plot. In this case, you're basically looking at the slope at what I would say
Unloading. Yeah.
Yes. So why is it so? Like, is there any specific reason or something?
Yes, because particularly what we have observed is that whenever we are doing tensile test and we are taking the slope from the loading portion of the curve, it's never actually correct. It takes into account the deformation encountered by the cross heads also. So in order to
Okay.
avoid that, we take the unloading modulus, which is relatively accurate than the loading modulus.
So this is the general process that we
Yeah,
usually follow for porous materials.
Not for the porous material. In fact, if I'm not wrong, it is followed for conventional materials also. If you want to really get the correct value of the modulus, it is preferred to do it for unloading side also, not the loading rate.
And what are these like 5.9 and 5.4% recovery?
Oh, these are the recovery strains that are observed after you are heating them. So here you are doing the experiment. I mean, loading them after at a particular temperature, and then after the unloading is done, you see that there